So I'm Volker, Thoughtworker and a developer, and we want to talk a little bit about continuous integration in the context of embedded software and share a little bit of the journey and the learnings and the experiences we had on my previous project, and it's still kind of Luca's current project.
So yeah, I worked with Volker on the code that I'm still on. He has escaped in the meantime. And in some ways, it's a very traditional software project, and in other ways, it's, for me at least, very new because I've never worked closely to hardware before. So yeah, well, what kind of project are we talking about? So this was for a client in the automotive space. So what they are trying to do is they have existing vehicles and they're trying to build, come up with new vehicles. And these days everything has to be connected to the cloud, so they wanted to follow suit. So actually make their vehicles sort of part of the IoT. The way they wanted to do this was to build a hardware module that they could both retrofit in existing vehicles as well as install in new vehicles that they're designing at the moment. So day one on the project, right? Everyone is eager, everyone arrives at the client side and everyone wants to get started. And what do you mean 3 months? And you're gonna see what this relates to in just in a second. Our goal was to build the software for this radio module, as we call it. And we already knew what this radio module was going to look like from the board specification. We were going to have an ARM Cortex-M4 CPU, and the radio module would be connected to all the other components in the vehicle using the CAN bus. For those who have never been in the automotive space, CAN bus is a rather old way of interconnecting components in vehicles. It has been around for quite some time. It's not exactly fun to work with, and it's people are trying to replace it, but it's still there. It's one of these legacy protocols that sticks around. Yeah, it also the module also has cellular and Wi-Fi, so we wanted to connect to the cloud in some way. So cellular and Wi-Fi was the way to go. And last but not least, the radio module also had Bluetooth. When we started the project, we didn't actually have any hardware. The radio module itself was still in the design phase, and it was going to be months until we had actual hardware in hand that we could test the software on that we would be writing. What we ended up picking up is a development kit, or as STM calls them, a discovery kit, with roughly the board specifications that we were going to have. So this thing didn't have a CAN bus, it didn't have all the connectivity stuff, but it did have the same architecture. So we were already able to essentially build Hello World and everything on top of that didn't use any of the connectivity that we're going to need. So essentially build a foundation for what we would be building on.
So, question is, what can we do right now? Because even these discovery kits are not available on day one, yeah? They have to go through procurement, and there's also some delay, not the kind of 3 months for the first prototype, but still some time to wait. So where can we actually start? There's also a huge cloud part, yeah? A lot of backend services and everything like that. And of course, we can just start there, setting up all the infrastructure in one of the cloud providers, setting up continuous integration pipelines, building the services in Java, stuff like that. If we would start to design the backend services and we don't have kind of the embedded software part that is supposed to talk to them, kind of how can we learn whether they work together? How can we learn kind of how the APIs would need to look like? One thing that we knew was that Cortex-M4, yeah? What we also knew from the specs is there will be some vendor supplied drivers and all that stuff to actually get that board operational. One other thing that was kind of pre-decided was that we knew that it was supposed to run FreeRTOS as an operating system. This is kind of a preemptive, more or less real-time operating system. And kind of what we wondered is, okay, we have our development machines, we have no hardware yet. Can we start to build something? Is there something that kind of simulates or emulates FreeRTOS on top of Linux, or in our case, Mac OS, making kind of use of all the POSIX functionality that is available and hopefully kind of matches the stuff that we would at some point get from the vendor. Then we could kind of introduce a platform abstraction layer that kind of encapsulates all the hardware-specific parts. This is something that we were actually writing. And then on top of that, we can kind of build our actual functionality, the actual software and features we wanted to implement. This immediately allowed us to kind of write this software on our development machines and run kind of the embedded software on our developer machines. And this allowed us to kind of get into the habit of test-driven development. Yeah, we could just use libraries like Google Tests or CPPU Tests. That's the one we were actually using. Writing tests, writing the features, and really get into that fast feedback loop. This also means we had some tests, which of course then leads us to setting up a build pipeline for our embedded software. Kind of we have all the typical stuff, some linting in the beginning, then compiling it. Everything runs on a developer machine, or in that case also somewhere in the cloud. And this already got us quite far, because we have kind of our basic tool chain set up. We have the continuous integration up and running, and we could restart quite quickly to implement features for the embedded software without any kind of hardware available at that point in time. One thing that we immediately added, though, was kind of this cross-compile part that you now see at the bottom. Because we were kind of using very recent compilers, but the cross-compile toolchain that we actually had that compiled to the target architecture, to this Cortex or ARM Cortex M4, was slightly older. So we really wanted to ensure that what we were building, the software that we were writing, would later on run on that device and will be compilable from that device. So kind of we set up a cross-compile toolchain, even though kind of the binary that came out of it, we could not yet deploy, but we'd still know that it would at least compile for that. And I guess everyone expected that this had to come, so we needed to Dockerize all the things. This software binary runs on top of Linux, yeah? So this means we can also wrap it in a Docker container and have the embedded software that it was supposed to run on some hardware within a Docker container, but this helped us by a great deal. What this allowed us is to kind of run them in concert and really have, we're using just Docker Compose, an RSpec, and another tool called ServerSpec, or library that integrates with RSpec. And this allowed us to build integration tests for testing our features, and in combination with all the cloud services we had. So this also allowed us to build the acceptance tests that we wanted to have, and also the end-to-end tests, which really allowed us to get some traction, get some speed, and getting the feedback that we really wanted to have. Eventually, the discovery kits arrived, and we were able to kind of fill that gap. This was kind of good for us because we could, for the first time, kind of verify all of our assumptions. Yeah, we had still a lot of assumptions going on, some decisions that we made, expectations about the hardware would actually behave. We could verify that our cross-compiling works, that the software itself, the embedded software, actually runs on some hardware. One other thing we could do now that we had hardware, we could also add some more unit tests to it that we could, at this point in time, execute directly on the hardware. This was really kind of a huge, well, this is now a huge jump in time. This took a little bit longer than the initially guessed 3 months before we got a hold of our first prototype. It was kind of basically working, didn't provide all the features. And we also kind of got the first vendor supply drivers for it. This was a point in time where we really, for the very first time, could verify that everything we did so far was actually working. We also wanted to have continuous integration using the actual hardware. So now I want to give you a quick overview with the test sub that we finally ended up with. On the right-hand side, kind of you can see a mini PC, kind of could be any. We ended up using Intel NUCs because we needed a little bit more power than, for example, Raspberry Pi would provide. On the left-hand side, we have our radio module. And now we have kind of different connections. The one that Lucas already mentioned is kind of the CAN bus. So we had a CAN adapter connecting to our PC, and this was also then going into the radio module. This allowed us to kind of send CAN frames back and forth between the radio module and our tests. We could also kind of record the CAN traffic, measure timing, stuff like that. The other thing that we needed was a J-Link. So this is something that you need if you want to flash your software on to the actual hardware. Then we had kind of a serial input-output. We mainly used this for logging, because sometimes it was hard to observe stuff going on the radio module because kind of the limited ways to really signal changes. We ended up adding a lot of logs so that we kind of can see the current state of the radio module, of the software in it. So this was also important for us. We have also relay control. This really allows us, for example, to power cycle the radio module, turn it on and off as part of our tests. And this is kind of the test setup that we ended up with, and we had kind of the entire thing bundled together a couple of times for the test setup, but we also had these for the developers. So developers could just take that entire cabling tree, connect it to their laptop, and do everything that the automated tests were doing also on their own machine when they wanted to test stuff or develop stuff. This is now kind of the setup on the, or in the center we have kind of the continuous integration server. It's GoCD that we have been using that kind of orchestrates all the testing and executes it and gathers or collects all the results and then kind of ends up with either red or green, yes or no. On the right-hand side, kind of you can see all the tests. It's not all, kind of just placeholder here. And on the left-hand side, you see the kind of this block stands for everything you've seen on the previous slide. And also here we ended up with having a couple of them because there were actually kind of not one prototype, but two. There were kind of different build-outs that we needed to test and support. So that's kind of the overall setup, and now we would like to go into some of the tests that we were running. It's only kind of 4 examples. It's by no means exhaustive even to what you could test, but also what we were testing, or what we are testing. So, first example. One thing that is important, kind of got reminded in previous session, is that you kind of need fast boot times. You can imagine kind of in the automotive context, if you enter your car and you want to operate it, you don't want to wait for any component to become operational. So we really had a hard time limit and that we wanted to measure. In our case, it was roughly kind of 1.5 seconds max. So we, under no circumstances, were allowed, our boot was not allowed to take longer than that. This was where we kind of were heavily using the relay board, really turning on and off the radio module, and then using the CAN adapter to wait for the first CAN message. There's kind of a very specific pre-operational message that kind of tells you, okay, I'm ready to go. And we kind of measuring the times and had kind of a check. If it's taking too long, then it's no. If it's kind of beyond that limit, then it's okay. But one thing kind of we learned, not immediately, but over time, that this is kind of just the tip of the iceberg. Kind of instead of just having this binary decision, yes or no, we learned that it's important kind of to really collect the metrics. How long do we need to boot? And really put that into a graph, because you want to see trends. When you're changing your features and extending your software, kind of the boot time changes. Yeah, it might become faster, it might become slower, but you really want to see and kind of correlate the feature you've been working on with the changes in the boot time. This is something not only in this context, but overall. If you have something like this, where it's kind of not binary, try to make sure to collect the metrics and put it on a graph so that you can really learn from it, but also, yeah, important thing is to correlate with the stuff you have been working on, the commits you have been doing, and see the changes. And with that, I'll hand over to Lucas to talk about the other 3 examples.
So testing can. Our dream scenario of how this would have gone was, okay, like we have a vehicle and we can attach, like we have this vehicle in our continuous integration setup and we can put it in our radio module and then just listen in on the communication between the two. Because the vehicle itself had a lot of other modules of all different kinds, like sensors, displays, battery, all kinds. And we wanted to make sure that they all interoperate, right? Unfortunately, these vehicles are sort of expensive and also physically kind of large. So it was difficult to get people to give them to us, and also it was kind of it would have been kind of difficult to fit them into the closet. So while we still have the dream of this happening, we currently our best result for this is to simulate the components that we integrate with, and just run them on the test agents that control the test run. For those who have interacted with CAN is sort of a complex protocol, and can open as a protocol on top of that protocol, which is also not particularly simple. So implementing this was a lot of back and forth and finding out the corner cases of how everything works. I think the only takeaway for us in this case is if you want to test things on the CAN layer, you should plan a bunch of time for this, because in the end you'll have to write the CAN and CANopen code yourself. This is from a recent debugging session that we had, and something wasn't working, and we were wondering why is this test suddenly not passing? And we had changed a bunch of the simulation code, and this interaction looks a bit like this. So, yeah, hello, I'm OX3D. Could you please transmit entry 2000 index 1? And then our simulated component responds, sure, mate, here's the data you requested. And then our radio module, which uses an open source implementation of the entire CAN stack, responds, oh no, you sent me the wrong data, abort. And then we respond, sure, mate, here's your data. So yeah, that didn't work out as expected. It took our debugging logs are actually in the form of huge hex dumps. So finding what went wrong when is sort of difficult. But yeah, that's sort of what it looks like to manually implement these protocols. Our long-running tests were essentially using the same simulated CAN scenario, and all of these, if this maybe I haven't made this clear, all of these use the setup that Volker introduced earlier. So all of these different connections, like the CAN controller, the J-Link, the relay board, etc. We wanted to see how the radio module behaves if you leave it on for an extended period of time and actually something happened. In this case, it was for 48 hours. So essentially, this was about flashing the radio module with the software and then leaving it running for 48 hours and looking how it behaved, continuously verifying whether or not, maybe it crashed because of memory leaks, or maybe it hard folded, sort of an exception. So just making sure that it runs without dying. Yeah, and the thing that we're doing at the moment is we're adding more simulation to it in order to more accurately simulate what this 48-hour operation period looks like. So to get it closer to reality. Yeah, where everything becomes full circle is essentially our end-to-end tests. We haven't talked a lot about the entire cloud component, but let's just assume it can do a bunch of stuff, and it's not really relevant what it does in this scenario, but we just have to assume that the radio module is connected somehow to this cloud. So one of our end-to-end tests looks a bit like this. The test agent tells the cloud, hey, can you please send this radio module a software update? And then the cloud will tell the radio module, hey, can you, here's a new update for you. Then the radio module will ask to the cloud to essentially able to retrieve the update via HTTP. Then it will install the update. And during the entire time this happens, the test agent will check, okay, has this software update been installed? And if it's installed within a certain time frame, then the test is successful, otherwise it fails. So this is an overview of the entire testing setup that we ended up with, that we have at the moment. This is still evolving constantly. But here you can see that we have, both of our builds are always running in the cloud. So it's very easy to pick a build from the cloud and then install it on, for example, on an actual vehicle and see how that works. So then we have the core tests that also run in the cloud. This is what Volker mentioned earlier. But then we also have a lot of PCB-specific tests that are much slower because they actually have to interact with the hardware. And for hardware, you cannot do stuff like mock out time, for example. So if something takes 500 milliseconds, you actually have to wait for 500 milliseconds. If you're doing that 1,000 times, then yeah, that just adds up. So I think the entire run of our PCB-specific tests is currently at 1.5 hours. Yeah, and in parallel to this, long-running tests which kind of run outside of the pipeline because they're taking too long. We have end-to-end tests, software update tests, all that kind of stuff. This is sort of an illustration of our journey when doing this. It certainly wasn't straightforward because most of us weren't very experienced in this particular area. But what we took away from it is that continuous integration for hardware is definitely possible, and it is very desirable because most of the cases it did lead for us to making a change and then immediately realizing through the testing setup that we had that this was probably not a good idea. It is significantly more expensive than if you're working with software. I think one of the test setups that Volker showed runs around 2,500 euros, I think. So if you have different models and different tests, because you want to have multiple of them because you want to have stuff running in parallel. So this quickly adds up to a bunch, amount of money that people are not willing to throw at you. One of the takeaways is also observing hardware is much more difficult than when you're writing a JUnit test, for example, because as I mentioned, you need to listen to the CAN traffic and see if anything goes wrong there. You need to look at the logs and look at everything is fine there. You might look directly in memory if something goes wrong there. That is also possible through the gelling, for example, but we haven't done that yet. If you've written a bunch of tests in any other software project, once you have the setup done, they're not very different whatsoever. Yeah, I guess it's somewhat similar to what testing in a mobile scenario would also look like if you're testing on an actual device. I was kind of looking for the weirdest PowerPoint slide animation that was around, and I chose this one. Yeah. That's it from us. Thank you.